Hello everyone, welcome to the Tim Booker channel. Wishing you all a pleasant listening experience. Today, the book I'll be deciphering for you is Immune. If asked, what defends our health? Many might answer with doctors, vaccines, medications, hygiene practices, and more. While not incorrect, the true hero of safeguarding our physical well-being is our diligent and often unnoticed immune system. To scientifically maintain good health, especially in navigating various risks, particularly during this era of pandemics, it's essential to truly understand our immune system. However, delving into the understanding of the immune system proves challenging due to the high threshold of knowledge in this field. The related disciplines are filled with daunting technical terminologies: antibodies, complements, interferons, alpha, beta, gamma, T cells, helper T cells, memory helper T cells, and the list goes on. Just memorizing these terms can be arduous. Moreover, the immune system's operational mechanism is incredibly complex. Its different components have distinct roles and functions that intersect and restrain each other. Additionally, numerous counterintuitive phenomena and exceptions further elevate the difficulty of comprehending the immune system. Nevertheless, the book Immune effortlessly elucidates the workings of the immune system in simple language. This ease stems from the author's professional background. Philipp Detmer, the author, is a German information designer and a popular science enthusiast. Since 2013, he has run his science communication channel, Kurz gesagt, in a nutshell, on the video platform YouTube, dedicated to conveying science in a simple, elegant, and understandable manner. The channel now boasts a subscription base of nearly 20 million. Detmer himself is an aficionado of immunology, having dedicated extensive time to studying the subject. At 32, he battled cancer, an experience that deepened his understanding and fascination with immunology. This journey led him to become a self-taught expert in the field. In this book, Detmer maintains his signature style, employing vivid metaphors and engaging examples to explain how the immune system works, making it particularly suitable for general readers lacking a background in this area. Through this book, we learn that the human body's immune system comprises multiple lines of defense, external barriers like skin and mucous membranes, coupled with innate and adaptive immunity within. Faced with invasions from bacteria, viruses, and various pathogens, the immune system activates different mechanisms for defense. When the immune system malfunctions, a myriad of diseases can afflict us. Without further ado, let's delve into the book's content through 3 sections. Firstly, we'll discuss the various lines of defense in the human immune system and explore the combat cells within them. Next, let's examine how the immune system safeguards us against different invading pathogens. Finally, we'll address the consequences of immune system malfunctions and strategies to boost our resistance. Let's start by understanding the components of the human immune system, specifically its defense lines and combat cells. For survival, organisms require energy. Some diligently produce energy, some acquire it through predation, and then there are others, like many bacterial pathogens, that prefer pilfering energy from others rather than producing their own. They choose to parasitize other organisms, but the hosts are naturally reluctant. Hence, to prevent invasion, organisms evolved immune systems early on. Today, our focus is on the human immune system, where multiple defense lines work within our bodies to ensure our safety. The first defense line comprises the skin and mucous membranes. Skin, despite its softness, forms a robust barrier due to its roughly 50 layers of stacked dead cells, resembling a thick fortress wall to pathogens. Moreover, it contains salts and various defensive chemicals from sweat, making it challenging for pathogens to breach, provided there are no wounds. Contrastingly, mucous membranes, located in the respiratory tract, lungs, eyelids, oral and nasal cavities, gastrointestinal tract, and reproductive tract, are more susceptible to invasion. Even though these are internal, they interface with the external environment. Unlike the skin, mucous membranes lack multiple layers of protection, being composed of a thin epithelial tissue. To resist invasion, the outer side secretes a mucous layer containing salts and defensive substances, while the inner side hosts numerous immune cells, serving as a defense against invading pathogens. Together, the skin and mucous membranes form the first defense line of the human immune system, deterring most pathogens from entering the body. However, even if pathogens breach this line, the body still employs innate and adaptive immunity. Innate immunity acts as the second line of defense, an inherent and universal defense mechanism. It lacks specificity but can broadly combat various enemies without targeted weaponry, akin to a novice toolkit in a game, basic but comprehensive. What combat cells constitute this toolkit? Let's introduce the main members, assigning nicknames based on their characteristics. First, the big eater macrophages, large immune cells primarily responsible for ingesting dead cells and invading pathogens. Then, the suicide squad neutrophils, fiercely aggressive combatants unbothered by self-preservation, capable of ingesting enemies or releasing chemical weapons through self-destruction. However, their aggressive methods often harm normal tissues. Additionally, in innate immunity, there's the patroller natural killer cells, constantly patrolling the body and eliminating potentially threatening cells that appear suspicious. These cells collectively form the primary killing force of innate immunity. Besides, there's a crucial but non-combatant member, the information officer, dendritic cells. They ingest and break down pathogens, analyzing their characteristics to dispatch intelligence for adaptive immune cell support. Adaptive immunity, the final defense line, activates when innate immunity alone cannot combat the enemy. Unlike innate immunity, it's not innate but evolves and strengthens throughout life, gradually waning in old age. While innate immunity lacks specificity, adaptive immunity compensates for it. It exhibits strong specificity against pathogens, developing tailored weapons against each invader, ensuring higher efficiency in eliminating enemies. The major players in adaptive immunity are the T cell and B cell families. T cells undergo rigorous training in the thymus, with only 2% graduating, ensuring their effectiveness without turning against the body. Mature T cells, including helper T cells, bolster innate immunity cells' combat capabilities and activate B cells for battle. Additionally, killer T cells can precisely eliminate infected or cancerous cells among the vast array of cells. Another crucial member of adaptive immunity is the B cell family, primarily responsible for antibody production. Antibodies, customized protein weapons, precisely eliminate specific enemies, akin to sniper rifles. Among the B cell family, plasma cells, derived from activated B cells, act as arsenal factories, rapidly producing antibodies. Both B and T cells form memory cells, such as memory B cells and memory T cells, akin to librarians, memorizing specific enemy traits and promptly responding upon reinvasion. Let's dive right into understanding the three lines of defense in the human body's immune system and the key cells that fight for us. Are you ready to explore how the immune system protects us against various invading pathogens? Many pathogens can invade the human body, but the primary ones are bacteria and viruses. Let's start with a scenario involving a bacterial invasion. Imagine stepping on a sharp nail that punctures your foot, allowing numerous bacteria to enter your body alongside the nail. The formidable barrier of the skin, which is usually impenetrable, is instantly breached, initiating a fierce battle between the immune system and the invading bacteria. But before the battle, a crucial question arises: how does the immune system differentiate between friend and foe? This is where a cellular structure, the receptor, comes into play. Receptors, a type of protein on the cell surface, resemble intricate puzzles, each having a unique spatial structure. Regardless of the creative adaptations bacteria may possess, they invariably require specific receptor proteins, similar to how all cars need wheels. The immune cells identify these specific receptors on the surface of bacteria to discern the enemy. Receptor proteins are referred to by different names in various contexts. On the cell surface, they are receptors; on pathogens, they are called antigens. When B cells release their receptors, these become antibodies. Despite the varying names, they are fundamentally proteins with distinct structures. With the ability to recognize friend from foe established, the innate immune cells spring into action first. The patrolling big eaters, macrophages, upon detecting bacteria, swiftly engage in battle, voraciously consuming the invaders. They also signal for reinforcements, calling upon their counterparts. In response, the suicide squad neutrophils ramp up their attack, devouring enemies and, in some cases, sacrificing themselves to unleash chemical warfare. Simultaneously, macrophages and neutrophils command an inflammatory response. While we've often heard of inflammation, what exactly is it? Inflammation is a common immune response to bodily damage caused by burns, scratches, bacterial or viral infections, and allergies. It essentially involves the deformation of blood vessel wall cells, allowing plasma to leak out of vessels and surge to the damaged or infected area. Despite causing discomfort like fever and swelling, inflammation aids the immune system in better eliminating the enemy. So, how does it assist? Inflammation has multiple effects. Let's highlight one: it supports the complement system. Part of the innate immune system, the complement system comprises over 30 different proteins that are typically dormant. However, upon encountering bacteria or viruses, it promptly activates nearby immune cells, guiding them to eliminate enemies. Additionally, complement proteins can combine to form weapons, puncturing bacterial membranes and expediting their destruction. Since complement proteins are abundant in bodily fluids, the presence of inflammation assists the complement system in functioning more effectively. In most instances, the combination of innate and adaptive immunity effectively blocks bacterial invasions. However, if the onslaught is overwhelming, the innate immunity signals for reinforcements from the adaptive immunity. The dendritic cells, serving as intelligence officers, tear apart the bacteria, collect their surface antigenic features, analyze their appearance, and then depart from the battlefield to the lymphatic network, a system comprising lymph vessels and nodes distributed throughout the body, where numerous adaptive immune cells gather. You might wonder why adaptive immune cells possess specialized ways to counter enemies. This is because the adaptive immune system harbors a vast repertoire of ways to counter foes. While there are potentially billions of antigens globally, equivalent to proteins, the human body doesn't remember the structure of every protein. Similar to how a chef uses a few ingredients to prepare numerous dishes, the immune system uses selected gene segments to create over 1 billion immune cells capable of recognizing different receptor proteins. Hence, there's always an adaptive immune cell tailored to tackle any pathogen. Dendritic cells locate these precisely matching immune cells, primarily helper T cells, and activate them. Notably, owing to the potent nature of adaptive immunity, the immune system ensures no accidental activation of adaptive immune cells, requiring a double confirmation during activation. Initially, dendritic cells present bacterial antigens to helper T cells. Subsequently, they engage in close contact to reconfirm the information's authenticity. Only then are helper T cells genuinely activated. Once activated, helper T cells rapidly proliferate and divide into two groups. One group heads to the site of infection to command the battle, releasing a series of chemicals significantly boosting the combat abilities of other immune cells, such as macrophages, while the other summons support from B cells. In the case of B cells, the activation process also occurs in two steps. B cells capable of countering the specific bacteria, upon encountering the bacterial antigen in bodily fluids, begin replicating and producing antibodies. However, these B cells won't exert their full potential without secondary activation. Only after receiving confirmation from helper T cells do most of the replicated B cells, known as plasma cells, swell and transform, efficiently secreting antibodies. After all this talk, what exactly are antibodies? They are also proteins, resembling the complement system. They're tiny and designed as weapons against pathogens. Yet, the fundamental difference lies in their specificity. While the complement system lacks specificity against pathogens, antibodies have a high degree of specificity, precisely targeting particular pathogens, thereby enhancing combat efficiency. Common antibodies look like small lobsters with two pincers, each capable of firmly grasping a bacterium. A multitude of antibodies can entangle numerous bacteria, with their tails sticking to other immune cells, facilitating these cells in swiftly devouring enemies. Thus, the presence of antibodies significantly enhances the immune system's ability to kill pathogens. With the cooperation of innate and adaptive immunity, invading bacteria are eventually eradicated. But what happens if the invaders are viruses? In such cases, how does the immune system protect us? It's estimated that about 200 viruses can infect humans, with the most common and lethal ones primarily entering through the respiratory mucosa. Let's consider the example of the influenza A virus and examine the circumstances that arise when these viruses invade our bodies through mucosal surfaces. The primary characteristic of viruses is their lack of cellular structure, forcing them to parasitize within cells for replication. They function akin to soldiers concealed within the Trojan horse, making it more challenging for immune cells to detect them. Moreover, viruses are much smaller than bacteria and replicate rapidly, copying themselves thousands of times within a short span. Faced with such cunning foes, how does the human body respond? We won't delve into the similarities between the immune system's response to viruses and bacteria. Let's focus on the differences. Firstly, cells detecting infection urgently release a series of cytokines, a group of proteins that transmit information. Among them, interferons are the most crucial as they effectively disrupt viral invasion and replication, alerting other cells to be on high alert. Subsequently, innate immune cells detecting abnormalities rush to the battlefield, macrophages start engulfing, neutrophils escalate inflammation levels, and they release a substance called pyrogen to induce fever. Fever serves as an immune strategy against viruses because higher temperatures boost the immune system's efficiency while reducing viral activity. Simultaneously, dendritic cells begin gathering antigen information, activating helper T cells. However, this time, helper T cells have an additional responsibility, activating their sibling, the killer T cells. Upon identifying virus-infected cells, killer T cells immediately issue orders for those cells to self-destruct, halting viral replication and spread. But here's the issue: viruses reside within cells, so how do killer T cells know which cells are infected? This involves a clever mechanism within human cells. Cells continually display recently synthesized proteins on their surfaces, akin to setting up numerous small display windows. If these display viral characteristic proteins, it implies infection. Killer T cells inspect these display windows to determine infection. However, some viruses are particularly crafty, destroying these display windows to evade detection. What happens then? This is where the natural killer cells, the inspectors of innate immunity, come into play. Their mission is straightforward: they only check if cells have these display windows. Cells lacking these displays are swiftly eliminated. This ensures that any virus attempting trickery won't escape the immune system's scrutiny. It's noteworthy that after eliminating enemies, the immune system still has work to do. Firstly, it shuts down the immune response because the immune system, being potent and potentially dangerous, tends to self-regulate. It consumes energy, and physiological processes like inflammation and high temperatures could harm the body. Therefore, the immune response tends to shut down gradually once the pathogens are eradicated, leading to the death of numerous combat cells. However, to prevent the pathogens from reinvading, some combat T and B cells remain, transforming into memory T and B cells. These act as librarians, recording enemy characteristics and remaining vigilant for the next invasion. Alright, we've discussed how the immune system functions under normal circumstances. But what happens if the immune system malfunctions? In the next section, let's chat about the consequences of immune system issues and how we can enhance our resistance. The immune system is a double-edged sword. Being too strong or too weak can have severe consequences. Let's begin with a scenario where the immune system is weak, using HIV/AIDS as an example. HIV targets the body's immune cells, specifically attacking macrophages, dendritic cells, and especially helper T cells. Once infected, these immune cells become targets for killer T cells. Given HIV's tendency to mutate, even if B cells produce antibodies against it, they often become ineffective against new strains. In the tug-of-war with HIV, the immune system weakens progressively, leading to AIDS in its advanced stages, where the immune system is essentially non-functional. Consequently, individuals with AIDS don't typically succumb to the disease itself, they perish due to various cancers, bacterial or viral infections, often a combination of all three. This is the consequence of a weakened immune system, leaving the body defenseless against internal and external threats. Now, what if the immune system is too strong? It might sound surprising, but the consequences could be more severe. Even terrifying viruses like Ebola typically take several days to claim lives, but an overactive immune system causing allergies could end a life in just 15 minutes. An exaggerated immune response to non-threatening elements results in allergies, somewhat like using a nuclear bomb to eradicate a cockroach in a room, an unnecessary overreaction. But why does this hyperactive response occur? The mechanisms behind allergic reactions remain largely enigmatic. Different individuals possess varying sensitivities to certain substances. When their immune cells repeatedly encounter these substances, they release a plethora of inflammatory cytokines, leading to allergic symptoms like redness, fever, and itching. If multiple body parts simultaneously react, it could cause a severe drop in blood pressure, even posing a life-threatening situation. Another issue that can arise within the immune system is when it turns against the body itself. As previously mentioned, T cells undergo rigorous screening in the thymus before deployment. Similarly, B cells also undergo such processes. This rigorous screening is a safety mechanism to prevent these powerful cells from harming the body. However, in some cases, the screening mechanisms malfunction, producing T and B cells that mistakenly identify the body as an enemy. If the double-check system also fails and these immune cells are accidentally activated, they attack the body's normal cells, leading to autoimmune diseases, which inflict prolonged suffering and, to date, remain incurable. Therefore, regardless of the issue within the immune system, the consequences are unbearable. How do we then take care of our immune system to improve its functionality? You might have seen numerous advertisements claiming their products strengthen the immune system. However, the truth is, all these advertisements are deceptive. Whether the immune system is too strong or too weak, it's not beneficial. Hence, striving to strengthen the immune system is a false premise. Our aim should be a balanced and stable immune system, one that strikes a balance between aggression and composure. Additionally, since the immune system is incredibly complex, with many mechanisms yet to be fully understood, there are no ready-made products in the market that can genuinely enhance it. The author suggests that to maintain a healthy immune system, we need a balanced diet, ensuring we intake various essential nutrients. Given the immune system's constant generation of immune cells, it requires energy to function properly. A balanced diet that includes fruits and vegetables provides the necessary nutrients for the immune system to function optimally. Besides, exercise also benefits the immune system. Even moderate exercise has its effects. Movement promotes the circulation of bodily fluids, facilitating immune cells and proteins to flow more efficiently. Additionally, the author recommends avoiding smoking and maintaining a happy and fulfilled mental state to minimize external disruptions to the immune system. So, we've covered the essence of this book. To summarize. First, we discussed the various lines of defense in the body's immune system and the different combat cells. The first line, skin and mucous membranes. The second line, innate immunity, comprising cells like macrophages, neutrophils, dendritic cells, and natural killer cells. The third line, adaptive immunity, including T cell families like helper and killer T cells, as well as B cell families like plasma cells and memory B cells. Next, we delved into how the immune system protects us from different pathogens. When faced with bacterial infections, innate immunity engages immediately, activating adaptive immunity when necessary. A collaboration among immune cells, complement, antibodies, and other proteins eliminates the invaders. In the case of viral infections, cells release interferons and pyrogens, while killer T cells and natural killer cells work together to eliminate infected cells. Finally, we discussed the consequences of immune system issues and ways to maintain resilience. A weakened immune system leaves the body susceptible to bacteria, viruses, and cancer cells. An overly active immune system can lead to allergic reactions, while the immune system attacking the body itself results in autoimmune diseases. The author advises us to focus on balanced nutrition, exercise, avoiding smoking, and nurturing a positive mental state to maintain a balanced immune system. Though we mainly discussed external bacterial and viral invasions, there's another internal enemy, cancer cells. These mutated cells continually emerge, but thanks to the immune system, we typically remain healthy for most of our lives. After hearing this book, it might be worth thanking our immune systems for their relentless efforts in protecting us every day. That covers the essence of this book. Congratulations on finishing another book. Thank you for your support and attention. Please subscribe to the Tim Booker channel, like, and share this valuable knowledge with your friends. Let's combine wisdom with practice to achieve our financial goals and create a better future. Thank you, everyone, and goodbye.